In this video, we're going to look at doing the random walk of some given object. This could be, for example, a particle such as a neutron. And we're going to combine together the idea of doing a random walk where we take a successive set of steps with the idea of making exponentially distributed size steps as part of that random walk. So first, I'm going to create a new script as usual from the command window. There we are. And I'm going to call this something like random walk in 2D, 2 dimensions. Put a few line breaks in and save it. Let's say random walk 2D. So to begin with, let's not have too many steps in our random walk. Let's say number of steps is equal to 10, say. And we wish to have a starting condition. Now, as you'll no doubt appreciate, this is probably not the most elegant way of defining things, but let's just define my starting x position as being at the origin and my starting y position as being at the origin. So clearly, if I wish to have a random walk with a number of steps, I need to have some kind of loop. So if I have 10 steps in total, then presumably I wish to go from I equals 2 to, well, let's make it from 1 to n steps. And I'll end there. So for each step, I wish to choose some kind of random direction. So a random direction in 2 dimensions is an arbitrary angle. So let's choose an arbitrary angle. We'll call that angle theta. And that angle will be somewhere between 0 and 2 pi. So to generate that, we do 2 times pi times rand. And if I want to take a random step of unit magnitude, then let's make the value of r, the distance travelled, equal to 1. So later we can change that. So for each step, I've now defined a value of r and a value of theta. So the step size in x and y, we'll call that dx, is equal to r times cos of theta. Remembering to check, if we need to, whether the cosine function acts on radians or degrees. In MATLAB it acts on radians, so that's the correct formula. And r times sine theta gives us the change in y. So in order to find out the position at the end of that step, we can say that x of I plus 1 is equal to x of I plus dx. That's nice and simple. And y of I plus 1 is equal to y of I plus dy. And that's it. That's a random walk with unit size steps. Now obviously I want to visualize that, so I put my trusty close all and clear all at the top of the script, and at the bottom I want to plot the x values versus the y values, and I want to join them because I want to see what that random walk looks like. So I'll do it in red, because red's my favourite colour, and let's see what it looks like. So I'll save that, and we'll run. That's what it looks like. And hey presto, we have a random walk in 2D. Now, let's increase the number of steps. Let's make the number of steps 50 rather than 10. We'll do that random walk again. And there we have a random walk of equal size steps. Now we want to combine that with some arbitrarily chosen step sizes. So let's put a mean free path in. So in my initial conditions, we'll do it at the top because that's some kind of parameter of our problem. We'll say lambda is equal to, say, 6, and I'll just put a comment, mean free path. And I wish to generate steps which are exponentially distributed. So when I generate each step, rather than having r equals 1, I wish to have the appropriate exponentially distributed sampling, which we looked at in the previous video. We can say lambda times log of a random number, and we wish to do minus that. Okay, so that this r value produces an exponentially sized step. So if we save that and we run it again, I have a random walk in 2D. So let's try that for a larger number of steps. There we go. Now the extension to 3 dimensions is relatively straightforward. What I'm going to do instead of having a theta and an r, I need a theta, a phi, and an r. So we're going to change the definition here because conventionally theta is defined as being the equivalent of latitude. So this is a value between minus pi and pi. So we can calculate something like it can go from 0 to pi, so that's pi times a random number. So we need to think about how we define what we mean by theta. Phi, on the other hand, is just the azimuthal angle, the longitude, and in this case I'm going to define it as 2 times pi times a random number again, and r was as it was before. So we need to now appropriately define a dz that goes with the dx and the dy, and let's try 10 steps up here again, and we'll say that z1 is equal to the origin as well. Of course we could start somewhere else from the origin should we so wish, and we wish to have a calculation down here, zi plus 1 is equal to z of I plus dz, and of course eventually I'm going to have to do plot 3 at the bottom, and we presume that we'll have to put a z there. We'll check that in a moment. So the only thing that's left is to calculate the correct way of converting the r, theta, phi values. So let's just clean up the code a little bit. We tend to say r, theta, phi, so let's calculate the r at the top and then calculate theta and phi. We want to correctly convert the theta and phi values that we've selected into the correct dx, dy, and dz values. So how will we do that? Well, there needs to be r at all points. So I'll put that there. So the height is simply going to be, that will be cos of theta in some way. Well, I think it will, in this case, if theta is equal to 90 degrees, then, or pi by 2, that will be a position at the equator, so dz ought to be 0 there. So it looks like dz in this particular definition should be cos of theta. And therefore the other ones, this should be sine of theta times cos of phi, and sine of theta times sine of phi. Let's see if that works. We'll try running that to see how that works. And well, it seems to be doing something. So we're not quite sure if this is working yet, so we probably want to look at this distribution of values. Let's increase the number of steps again. Let's make it 100 steps. So it seems to be doing something. We can rotate this plot in 3 dimensions. If you can grab it there, there we are. So it looks like it might be a random walk in 3D. How can we check this? Well, let's take this code that we're using here, and rather than plotting the random walk here, let's just create a set of points on a sphere and see if those points actually do lie on a sphere as we would hope them to do. Because remember, we're trying to represent a random walk where we're taking some value of r which is exponentially distributed, but we have an arbitrary direction. So let's grab all of this code. So I select all and copy. I create a new script and I paste the code back in. So rather than plotting, so I probably should call this, we'll call this isotropic distribution in 3D, and we're going to plot n points rather than n particles, so we'll put n points down here, and we're now just going to plot points on a sphere to represent the set of directions that we're trying to generate. So it doesn't really matter what r is, so let's make that 1, and now we simply want to generate an xi value, a yi value, and a zi value for each of those 3 points. So you can see that I'm trying to generate points on the unit sphere which are randomly distributed. So obviously we need to delete this. So these points are no longer connected, so we'll just make those dots, and we'll save that, and we'll call this isotropic distribution in 3D. Let's say that 3D, something like that. There we go. And we'll run this and see what it looks like. There we go. So there are some points. Let's increase the number of points that we're using. Let's shrink this window to make it a little quicker to display. So we'll have 1,000 points instead. Save and run. And oh, it's looking a little bit better. Now we can spin these points around. There we go. Now you can see as I spin these points around, there seems to be some kind of problem there. Let's increase the number of points to 5,000, and we'll run it again. Note, by the way, that this lambda here isn't doing anything. We can get rid of that later. So we can generate points on a sphere, but the points are actually not uniformly distributed. As you can see there, the points are clustered more towards the poles than they are towards the equator. So we're choosing a random direction, but there is a bias towards the North Pole and the South Pole of that sphere. And of course the answer is, the reason why this is occurring is because whilst the value of phi that we're generating is uniform, and therefore this is correct, this value of theta, the way I'm generating it, results in a clustering of the points. Imagine if I have a large latitude somewhere to, say towards the North Pole or the South Pole, then I am generating an equal number of points at those large latitudes as I am near the equator. This is similar to the idea that the lines of longitude are getting closer together at the poles than they are at the equator. So what I need to do is I need to correct that density appropriately by not using this calculation, but by using something else. So I'm going to leave that as an exercise. We need to do something which is going to be an inverse cumulative distribution function method. So rather than sampling uniformly across theta from 0 to pi, we need to calculate something different. So I'll leave that for the viewer to figure out how to do that. But nevertheless, we've got something which is basically correct. We have a random walk in 3 dimensions. So in fact, I've now changed what this is. This is now a 3-dimensional random walk. So just to recap, in fact, what I should do is save it as a new, save it as a random walk 3D. Okay, so I've overwritten the old 2D code, but you can see how it worked. And if I increase the number of points here, just to recap, what are we doing? We're generating a random direction, remembering that this line 20 here is not giving me an unbiased random direction. There's actually some bias towards north and south, so this is actually incorrect. But this is generating something like a random direction. We're generating an exponentially distributed step here, and then we simply combine those together to make the dx, dy, and dz that represents the movement of the particle at each step, and then we're simply generating where that particle moves to from one step to the next using these 3 lines of code here. And we can run that, and there's our random walk. And as you can see, it's apart from that lack of uniform angle of theta, okay, it's not giving us quite the right isotropic nature. We can fix that later. This is giving us a nice random walk in 3D.